Okay, so we'll get started. I'm guessing everyone can hear me.
Yes, sir.
Yeah. Okay, so we will continue our development of the Fourier analysis. So let me just briefly mention what we have done in the last two classes. So we first talked about Fourier series, in which a periodic signal with a period of t can be represented as a sum of an infinite number of sinusoids, complex exponentials, which have a period of a frequency that's the multiple of the fundamental frequency, which is 2 pi by t. Okay, so so k0 is just the DC. So that's for that phi k t is just 1, but otherwise it's going to be 2 pi by t, 2 times 2 pi by t, 3 times 2 pi by t, and so on. So these are the analysis and the synthesis equations for the Fourier series. Oops, sorry, there is a pointer. Okay, so and you can see that this axis, the frequency axis, is discontinuous. You get frequency values only at a discrete number of points. Although the number of points is infinite, it's 1, 2, 3, 4, it's countably infinite in this case. So that was the Fourier series for periodic signals. And we did an example, looked at certain properties, and then we talked about its discrete counterpart, the discrete Fourier series. A discrete Fourier periodic signal is a signal that repeats after every n samples. And there we defined the basis functions in a similar way. So these are multiples of the fundamental frequency omega naught, in this case given by 2 pi by n. However, if once defined this way, it's easy to see that you don't get an infinite number of distinct basis functions, you just get n. They start repeating after n. And we proved that also. So the signal, when it comes to a discrete Fourier series, can be obtained like this. It looks very similar, but now to the previous case. But instead of an integral, we have a sum here, and you just need to sum over n distinct values. Okay, and likewise, if I give you those n coefficients, I can synthesize xn back using this formula. So this is the synthesis and the analysis and synthesis equations for discrete Fourier series. And in both cases, the proof is actually very straightforward, and it relies on the fact that it's just based on this in the continuous domain, which is that if it's a continuous exponential, complex exponential, the integral over any period is just 0 unless this thing itself is 0. Okay, in that case, it's t. So this was the proof that I used to prove this, and its discrete counterpart is this equation here. Can actually be very easily proven using geometric series. You can take e to the power jk 2 pi by n as some number r. So you can just see then it's r to the power 0 plus r to the power 1 plus r to the power 2. And it will just become r0 1 plus, so it will become 1 minus r to the power n divided by 1 minus r. But you will see that the numerator will become 0. Okay, unless the term here is a multiple of n to begin with. Okay, so or you can think of this as a bunch of vectors that are spanning your phase space from 0 to 2 pi, and their sum is 0. And that's the interpretation that we used in the last class. But basically, at the end of the day, these are the two things that are needed to prove the continuous and discrete Fourier series expansions. Okay, and then we did some properties, and now we are ready to talk about the Fourier transform. So before I move on, are there any questions? Okay, so if there are no questions, I will move on and now talk about aperiodic signals. Aperiodic signals for which we compute what is called the Fourier transform. So what if the signal is not periodic? Well, the answer is that it can be considered as a signal which has a very, very long period, infinitely long period. Okay, and in a Fourier series representation of a periodic signal, as the period increases, as t increases, fundamental frequency 2 pi by t decreases, and therefore the harmonically related components become closer in frequency. So as the period becomes infinite, the frequency components will become infinitely close and essentially form a continuum. And the Fourier series sum becomes an integral, and that is what the Fourier transform is. Okay, so let's look at this using an example that we have done previously. So suppose xt is 1 over this interval between minus t1 and t1, and it's 0 between t1 and t by 2, after which it repeats. So it's a periodic signal. For a periodic signal, I can compute the Fourier series. Okay, this is a continuous periodic signal. So I compute the Fourier series, and the Fourier series coefficients are given like this. It's actually the integral is from minus t by 2 to t by 2, but it's 0 here. So it just becomes minus t1 to t1. And if I solve this, I end up getting this. This we have done previously. I had shown you when we had first, it's the same as this. Now, here's how I'm going to plot it. Remember that AK shown here is 2 sine k omega t1 divided by k omega naught t. This is obtained by just solving this. Nothing, it's very straightforward here. So don't worry about this. Just look at that and think of the coefficient as a sample of a continuous function given by this. Okay, so k omega naught could be written as some omega. Okay, you take the t on this side, so it becomes tak. And then tak is just 2 sine omega t1 divided by omega at omega equal to k omega naught. Okay. So this 2 sine omega t1 by omega could be thought of as a continuous function in the frequency domain as a function of omega. Okay, so as a function of omega, this line here is just 2 sine omega t1 by omega. And you can think of just sampling this function at some value given by k omega naught. Okay, and what I'm showing you here is the Fourier series coefficients and their envelope for the periodic square wave for several values of t with a fixed t1. So this is t equal to 4t1, this is t equal to 8t1, this is t equal to 16t1. Essentially what is happening here is that these guys are just progressively moving farther and farther away. And what you see here is that in effect, it just gives you the coefficients at closer and closer points. Remember, omega naught is 2 pi by t. So it's now reducing and reducing. And essentially at the limit, it will just become infinitely close. And you'll end up getting a frequency representation, which is this continuous function given by this formula. That's essentially the periodic extension of an aperiodic signal. Okay, is this fine? Can I move on? So let me just show you this mathematically. It will probably make more sense there. So I've got a periodic signal. I've got a finite length signal here, which is restricted between minus T1 and T1, but it's not periodic. It's zero everywhere else. So it's a finite length signal. And I'm going to make a periodic signal out of this. So this is an aperiodic finite length signal, and I am making a periodic counterpart of it, which is equal to xt over one period. So here and here for over this period, it is minus t by 2 to t by 2, it's the same. But then this one has copies of this. Okay. And now I'm defining a continuous function x of j omega given by this formula. Okay, it's the integral of xt multiplied by e to the power minus j omega t dt. This is my definition. So based on this definition, if I now look at this periodic continuous signal and ask what is the Fourier series coefficient of this, that is going to be given by this formula here, right? So Fourier series, let me just, it's easy to get lost in these things. It's just this. It's the same, but it's at a particular frequency, k omega naught. So in this case, it's nothing but ak is nothing but of this periodic signal is nothing but a sample of this continuous function at k omega naught. Okay, so if you put j k omega naught and divide by 1 by t here, you will get ak. So ak is just 1 by t and you take a sample here. That's it. Okay. And then if I get all these coefficients, a1, a2, a3, up to, from minus infinity to infinity, I ask how am I going to reconstruct my periodic signal back? It's given by this synthesis formula. So the x tilde t is an infinite sum of ak multiplied by what the complex coefficient is. This is just the Fourier series expansion of the periodic signal. Okay. And then I divide by 2 pi and multiply by 2 pi here, and note that 2 pi by t is just omega naught, and I write this way. So x tilde t is 1 by 2 pi summation of k going from minus infinity to infinity of a sample of this continuous function given like this multiplied by e j k omega naught t d omega naught. So let's think about what happens here now as t starts to increase. So I'll get to this part in a bit. Let's just think of this. So I've got a continuous function here, which is this function x of j omega. And I'm looking at an infinite sum of x of j k omega naught. So it's particular value here. Okay, multiplied by e to the power j k omega naught t. So at k omega naught t, you've got e to the power j k omega naught t. It's this thing multiplied by, this is your k plus 1 omega naught. So this little bit here is omega naught. It's the same as this. So this is an area given by this little box. And you've got infinite such boxes. And the integral here, the summation here is from minus infinity to infinity. So the overall area is just the sum of all these boxes. This is quite important to understand. Is this okay with everyone?
I don't understand.
Okay, so where shall we start from? Is this okay?
Yes.
This is fine, right? So what I am doing here is going back to my discrete Fourier, there's no discrete here. So this is all Fourier series. So I'm going back to this. Okay, so if it's a periodic signal, I can represent it as a sum of an infinite number of complex exponentials with frequencies that are multiples of the fundamental frequency. And the coefficients can be obtained by taking the integral over a period of x after multiplying it with e to the power minus j k omega naught t. That's how you get ak. As you change k here, you get different coefficients. I'm just going to apply this logic here. Same thing. So I'm looking at the continuous signal here. Okay, sorry, the continuous and periodic signal here. So I have got a signal xt, which is only between minus t1 and t1. So I am going to make copies of that and make a periodic signal out of this. 1 second. So this is a periodic signal. And because it's a periodic signal, I can take its Fourier series. So the Fourier series is going to be given by ak using my previous formula is just one period of the integral of xt, sorry, in this case it's x tilde t, multiplied by e to the power minus jk omega naught k minus j omega naught k t dt. This is the Fourier series, right? This is what we, just the previous formula. And notice that if I define, this is a definition here. I have defined a function which is, sorry, here it's going to be minus infinity to infinity, which is defined this way. Then ak is just 1 by t and this function at jk omega naught. Okay, so omega is a continuous variable. I can put whatever I want here. If I put k omega naught, this thing here becomes j k omega naught like this. And within one period, x tilde t and xt are the same. And after that, it's 0. So this whole integral is the same as this. Integrating xt over minus infinity to infinity is the same as integral x tilde t between minus t by 2 t by t2 to t by 2. So ak is just this. Is this fine? Is this okay?
Yes.
Yeah. Okay. So now that we have got the coefficients, we are going to ask how am I going to construct x tilde t from the coefficients? And that gets back to the synthesis formula, the synthesis formula, where xt can be obtained by summing all these coefficients, ak's, and multiplying it by e to the power jk omega naught t and taking the sum from k of from minus infinity to infinity. This is the Fourier series synthesis equation. So if I do this, this little thing is just ak. So ak e to the power j k omega naught t multiplied by ak, and an infinite sum gives you this. This is just the Fourier series synthesis formula. By definition, no tricks here. I have just used ak as this. Okay, and then all I have done here is divided by 2 pi and multiplied by 2 pi. So I do 1 by 2 pi here and a 2 pi here, and note that 2 pi by t is just omega naught. So I just put that here. Okay, and now what I want you to think of is what is this whole expression as omega naught becomes smaller and smaller. Okay, and that is what we are doing here. This function is your continuous way. So this axis is omega. It's not t now, it's omega axis. This is the continuous function that I have given here, x j omega. Okay. And then x of j k omega naught is just the value at k omega naught. This little point is x of j k omega naught, like here. Correct? I'm just putting the value of k omega naught, omega equal to k omega naught. And then this function, if you now call it e to the power x j omega multiplied by e j omega t. Okay, so this function is now x j omega, which is a continuous function, multiplied by e j omega t, which is also a continuous function. Then this sample here is just this. Okay, and this little area here, which is which has a step of, so this little point here is k plus 1 omega naught. So this is has a width of k omega naught. So this area is just this whole thing here. And therefore the sum is just the overall area of an infinite number of little pieces like this. This sum is very close to the overall area as long as your omega naught is very small. Omega naught is just the fundamental frequency given by 2 pi by t. Is this fine?
Yes.
It's okay, right, everyone? Just some people say yes, so that I feel more comfortable. Is this okay, right? Okay. Somebody else said yes. Do I need to repeat this again? Okay, I'm going to move forward. Okay, so people who are confused, I'm sure some of you are still confused. This is confusing stuff because there are lots of slightly different Fourier expansions, and they are interrelated in somewhat confusing ways. So there's no way around this. You just have to spend a lot of time. There's no other way around it. It's not easy to understand it in a short duration of time. People takes like several courses worth of stuff before this really settles in. So you'll have to go back to Oppenheim and Wilsky and carefully read the section. It's very accessible. You don't need any prior knowledge, but you have to spend several hours on this for this thing to settle down. Okay, And please do so now, because we'll be moving forward somewhat quickly. So please go back and read this if you are still confused. So let me just summarize. I've got a periodic signal x tilde t. Because it's a periodic signal, I can take the Fourier series. This is the Fourier series synthesis equation, which is just a sum like that. This is just AK, which I'm defining as a sample of a continuous function given by x j omega. And then this summation can be thought of as, so this line here is just x j omega e j omega t. So it's a continuous line because it's a continuous function of omega. So I'm just taking samples of this continuous function at k omega naught. Okay. And multiplying by omega. So any one sum here of this infinite sum, any one sum is one little piece given like this. Okay, it's just x jk omega e jk omega naught t, which is this thing here multiplied by omega naught. And then as t approaches infinity, your omega naught becomes smaller and smaller until eventually this becomes the integral. The summation is replaced by the integral, and your omega naught becomes delta omega, d omega, given like this. Okay, so essentially it's the same thing that I had shown earlier. This thing, coefficients becoming closer and closer until it becomes a continuous function itself. And if you look at the coefficients, a case, it's one period of this continuous periodic signal, but this is the same as taking xt over one period, because over that period it's just x tilde t is just xt. Within t by 2 and minus t by 2, they are the same. But you can integrate it from minus infinity to infinity also, because xt is 0 everywhere else. So the analysis equation, getting the coefficients, can be obtained like this. And in the limit, k omega naught becomes a continuous variable omega, and I am left with this formula here. Okay, and this is the Fourier series. This is the Fourier series analysis and Fourier series synthesis equations. Now notice that both are continuous. Xt is a aperiodic signal for which you can compute a continuous representation in the frequency domain given by this formula. And this is your Fourier transform. Okay, so now this is the third one that we have done. We had Fourier series, which is signal is continuous, the coefficients are discrete. For discrete Fourier series, in which the signal is discrete and periodic, and its representation is discrete, and both have a length of n. And now Fourier transform, which is a continuous aperiodic signal whose Fourier representation is also continuous. You need an infinite number of frequencies to represent the signal back if it's not periodic. Any questions? Okay. So let me just show you this with an example. So again, there are these convergence issues. Am I always guaranteed that if I can compute x j omega and I put it like this, can I recover the signal back? The answer is no. Like my previous case in which I was talking about convergence, like my the previous before that I have talked about convergence issues. So turns out there are certain conditions that xt has to follow in order for this whole thing to work. And in general, convergence can be obtained, which means that this will work if xt is square integrable, which means that if I square the signal and integrate it over minus infinity and to infinity, it should be a finite number, can't be infinite. Then this representation will converge to the original signal in the mean square sense, which means that the energy of the difference will go to zero. Okay, so we are not dealing with convergence in this class. It's a little bit more involved. All the signals that we are going to deal with won't have any of the convergence issues. So we don't really need to worry about it. I just wanted to quickly mention that here, that for this whole thing to work, the signal should have finite energy. Okay, so let's look at an example. And this is the same example as before. T is 1 for t less than t1, and it's 0 everywhere else. Notice that it's no longer a periodic signal, it's an aperiodic signal. And then x of at j omega, this is now a continuous function, is just you put this formula here and you just make it 1 between minus t1 and t1, and you end up getting this. Does anyone know what this function is called? It's a very popular function. This is what is called a rect function, and its Fourier transform is called a sinc function. Okay, and they actually go back and forth. If you have a sinc function as an input, its Fourier transform is going to be rect. Okay, so I'm going to talk about properties of Fourier transform, which are very similar to the properties of Fourier series. But before that, there's one question that I have, and let's see what we can do here. So suppose let's take an example in which xt is a sinusoid. So xt is equal to sine 2 pi omega naught t. What do you think is going to be the Fourier transform?
Not so sure, but I can just say that if we try to take the integral, so the limits will be like 0 to 2 pi because of the
No. There's no 2 pi here. It's this is the Fourier. It's minus infinity to infinity.
Uh-huh. Okay, so no, let me try again.
So xt is some sine 2 pi omega naught t, and you multiply it with this and you take an infinite integral. What are you going to get?
I think delta function omega minus omega naught.
Okay, how are you getting a delta function?
I don't think.
By doing this integral.
Intuitive answer, not.
Huh?
I have not thought about it.
Okay, so the answer is that it's a trick question. Fourier transform doesn't exist for periodic signals, strictly speaking. Remember, it has to be a periodic, aperiodic and finite energy signal.
It won't have finite energy, right?
It doesn't have finite energy. It's it has infinite energy and it's periodic. So you can't take the Fourier transform of a sinusoid, strictly speaking. However, there is a hack here that people use. It's in fact what is called a generalized Fourier transform, which allows us to represent sinusoidal functions also. And I'm going to tell you about the hack before I get to the properties. And the hack is this. Suppose I have a delta function sitting at omega naught. And I ask, what is a signal whose Fourier transform is a delta function sitting at omega naught multiplied by 2 pi? If I do that, so I am now finding xt. I'm using this formula here. And finding xt given x omega is a delta function sitting at omega naught. So I put, this is your the x omega, xj omega, right? It's just this. And when I integrate it, you can see this is the shifting property. This gets cancelled. And then delta function, whenever you integrate it with any function, just takes the value of wherever the delta function is. So you get back this. Okay, and this is a a complex sinusoid. This is E cos omega t plus j sin omega t. So even though, strictly speaking, you cannot take the Fourier transform of a sinusoid, nonetheless, a sinusoid can be thought of, or complex sinusoid can be thought of as a delta function in the frequency domain. Okay, so if I give you a sinusoid using this generalized version of the Fourier transform, you can always think of it as a delta function sitting at omega naught. And in general, if I've got a bunch of delta functions sitting at multiples of k omega, so I get a bunch of delta functions of different amplitudes given by ak, and I take the sum, the generalized Fourier transform gives me this signal back. Okay, this is just, I have just used this shifting theorem under this summation and got ak and jk omega naught. And now going back, if I have got a periodic signal, so if xt is periodic with Fourier series coefficients ak, this, remember, is just the Fourier series expansion of xt. This is how you would expand it using Fourier series. Then its generalized Fourier transform is essentially a bunch of delta functions sitting at 0, k omega naught, omega naught, 2 omega naught, 3 omega naught, and so on, whose magnitude is given by ak. This is the expansion. So even though I cannot take the Fourier transform of a periodic signal, I can take its Fourier series instead, get the coefficients, and think of the Fourier transform representation as a bunch of delta functions sitting at multiples of omega naught with coefficients given by AKs. Okay, does that make sense? This thing is actually very handy for us to be able to go from to get the Fourier transform of one very important function, which I'm going to talk about next. But this is this concept clear that in general you cannot take the Fourier transform of a periodic signal using standard formula? This doesn't work, but I can hack the system and I can take the Fourier series coefficients, and then the Fourier transform can be thought of as, it's still continuous in frequency, but it only takes values at multiplus pulse of omega naught. It's zero everywhere else. But at these values, there's a delta function whose coefficient is AK, which you obtained from your Fourier series.
Sir,
Yes.
so can this concept be applied in the case of neuroscience? So like when the neuron has a oscillatory pattern, finding pattern as an oscillation or everything. So does this concept are applied there or not? It's just
Yes, it is applied.
so there we assume that if it's an oscillation, so it is a periodic, but then we convert it into a generalized Fourier transform.
Yeah, well, turns out, when you're doing signal analysis of the type of signals that we are doing, you all need to first convert it in the discrete domain. And some of these issues just trivially go away once you go in the discrete domain. But yes, if you were thinking of it as a periodic oscillation in the continuous domain, then its Fourier transform would have a delta function. We'll see that the delta function in the discrete domain is easier to deal with. So you don't run into this problem when you do the actual signal analysis. But this is an important step that we will need to go from continuous to discrete, which is why I'm just telling you right now. Okay, so this is the thing that I really want to talk about, because we will find it very handy. This is what is called a comb function, or an impulse train function. It's nothing but just a bunch of delta functions separated by a period of t. So it's a continuous periodic signal. Correct? Now I ask, what's the Fourier transform of this? And you will say, okay, it's a periodic signal. So I need to take the Fourier series first. The Fourier series is just this, which is just 1 by t. It will just, so I Fourier series, I integrate over one period, minus t by t to t by 2. So there's a single delta function there, right? And irrespective of what the value of k here is, the integral, because the delta function is sitting at 0, is just the value here at 0, which is 1. So this integral is just 1. So the coefficient is just 1 by t for all k's. So the generalized Fourier transform is now a bunch of delta functions sitting at 2 pi by t, 4 pi by t, and so on. Omega minus these, this is where your delta functions are sitting. There are an infinite number of them, and each one has coefficient of 1 by t, given like this. So I have just used this formula, and from there I have got this, and AK is just 1 by t. So this is 2 pi by t comes out, and I'm left with the delta function here. So always remember, if you have a comb function as an input, you get a comb function as an output. the closer the delta functions are in the time domain, the farther apart they are going to be in the frequency domain. Okay, so when these guys bunch together, 2 pi by t becomes large, 1 by t becomes large. So these guys go quite far. Likewise, if t is large, then 1 by t is small. Okay, and we'll see that when we try to sample a signal, so I've got a continuous signal and I want to look at certain samples of it, I can always think of it as a product with a comb function. The comb function is 0 everywhere, but it takes a delta function, positive value at the delta function. So a sampled signal is just the product of a continuous signal and a comb function. And therefore, in the frequency domain, it's just a convolution of the Fourier transform of the continuous function and the Fourier transform of the comb function, which is again a comb function. Okay, so that's why we are talking about all of this. This comb function is going to be essential for us to understand how the Fourier representation changes once you sample a signal. Okay. Any questions on this? So I see a lot of stunned silence now. I think you guys are all busy with the homework assignment, so maybe you haven't, some of you haven't followed this up. Please go back and read this carefully. Okay, it's easy to get lost otherwise. You won't gain much out of the class if you are not reading these sections. Now that the homework is out of the way, once you read this a few times, it will make sense. It might look a little bit overwhelming, but the text is very well laid out. So please do that. Okay, so this will all fall in place. And once it falls in place, it looks so nice that you'll be very happy. But it is a bit overwhelming. So, so you'll have to go back and read all of this. Okay, so I'll finish off Fourier transform just by talking about the properties. And turns out the properties are exactly the same as what we got with Fourier series. Okay, so all these little things, linearity, time shifting, it's just that there were AKs and these were discrete. Now it has all become continuous. But otherwise, the properties are very similar. And as before, let me just talk about one property which is very, very important, which is this here, that a convolution in the time domain corresponds to a multiplication in the frequency domain. Okay, so in the discrete Fourier series, in the Fourier series, we had looked at this one, where a product in the time domain become a convolution in the frequency domain. It also holds in the, in the Fourier series, this opposite one. But let me just prove this one to you. It's very elegant. So here it is. I've got a signal y, which is a convolution of x with h. So this is the convolution formula. It's a convolution formula here. And I want to find out the Fourier transform of y, which is given by this. We also write it as Fourier transform of yt. And what is that? It's just minus infinity to infinity. You put yt here, e to the power minus j omega t dt. This is almost by definition. Now there are two integrals, one that's integrating over tau, the other one that's integrating over t. So I just do the integral over t first. So x tau goes out, d tau comes here, and everything that is dependent on t comes inside the inner integral. So it's h t minus tau whatever I had done here, I have just taken e to the power minus j omega t inside dt. Okay, now I use the time shift property and note, oops, sorry, this one, that if I shift something in time, the frequency representation just has e to the power minus j omega t naught multiply with the same thing. So apply the same logic here, and this becomes just the Fourier transform of h with this little factor here because the time is shifted by tau. So I put that inside, and now it's an integral over tau. This is just a function of omega. This comes out, and I'm left with x tau e to the power j omega tau d tau, which lo and behold is just the Fourier transform of x. So y is just the product of h and x. This is an awesome property because the convolution in the time domain becomes a product in the frequency domain. Okay. So that's this property here. Convolution in the time domain is a product in the frequency domain. And we'll wrap up by doing again the Parseval's theorem. And this is what I was telling you earlier. This is signal energy in the time domain. Energy. You square the signal and integrate from minus infinity to infinity. That's the energy in the signal in the time domain. This is the energy in the frequency domain. X j omega is Fourier transform. It's continuous in the frequency domain. And you take the mod and square it and integrate over frequency. And these two are related. This is the Parseval's theorem. It says that the energy can be either represented, integrated over time or over frequency. They're equivalent. And how do I prove it? Now, if I look at the left-hand side, it's just xt multiplied with its conjugate here. And then I'm just going to put x star t as this. This is directly coming from the Fourier. This is the synthesis equation where x tilde t, x star t is given by just this. I just integrated x j omega with this and integrated to get this. So this little thing here is this. Okay, and again I can take this out and integrate over t first, take everything that is a product of that involves t here, and when I get those terms, e to the power minus j omega t and xt that comes here, this thing is just now x j omega. And therefore, this is just the product of x star j omega with x j omega, which is this. Okay, so Parseval's theorem, this is the other important relationship for aperiodic signal. The integral over time is the same as integral over frequency. And this is actually how we compute the energy of the signal. Okay, folks. So we have finished Fourier transform also. This is continuous in time and discrete in frequency. Time and frequency. This is continuous in both. This is discrete in time and discrete in frequency. And we'll look at, this is this. And we'll now look at the DTFT in the next class, which is this. Discrete in time and continuous in frequency. And then we'll finally get to this, and that will be it. Okay, there are any questions? I'll take them now. Otherwise, the class is over.
Sir,
Yeah.
I have a slight doubt. So, maybe you might have explained it before also, but